Hello everybody, and this is a packet of multiple choice questions on stoichiometry that you should have received in class not too long ago. This is a compilation of multiple choice items from over the course of about 40 years in old exams, as you see at the top of the document there from 1970 to 2010. What I want to do in this video is simply choose 10 of the questions included here and work through them, focusing on mental math and some strategies for that. I've chosen the 10 here at the top of the screen, number 3, 4, 5, 8, 12, 20, 23, 36, 37, and 41. And the numbering on that, I've just gone through, and I think we've done this in class with you. If not, just going through and numbering the items from start to finish, disregarding the numbers that were on the original items from the various years, just because it's rather random, and there's some duplicates as well. So if you haven't already done so, make sure that you go through and number. You should get, if you do the whole packet, as I've got it printed here, you'll have 43 questions altogether. And again, we're going to focus on 10 that I picked out that have various mental math skills that are important to be able to kind of get a start on and eventually hopefully master, as well as maybe some other tips along the way to help you out. And we'll see how long this video gets, if we can squeeze all 10 into one video without getting too crazy long. But as always, feel free to watch as much or as little as you like with the time that you have. So the first one here, number 3, asks about the moles of oxygen needed to produce 14.2 grams of P4O10 from phosphorus. Now keep in mind throughout our multiple choice work here that we don't want to be using the calculator, because we're not going to be able to use the calculator on these come exam time. And you should have your periodic table nearby. I've got it off to the side over here, so we'll use that as needed, and refer to some numbers on there that along the way as we go, along with that mental math stuff. So for number 3, they're talking about a reaction here. It's important that we identify that they're talking about a reaction. You don't need to know about the type of reaction per se, but we do want an equation. We're taking phosphorus and oxygen and combining them. That's right there in the context of the question. How much oxygen is needed to produce P4O10 from phosphorus? And so the idea that the suggestion then is that we can add oxygen to phosphorus and make P4O10. Well, there's the equation. It's a relatively simple synthesis reaction. We want to be able to get that balanced, because if they're talking about relating 2 or more substances, as we are in this one, then certainly we're going to need to have an equation and have it be balanced. So there's our equation. The other strategy is always, in most problems, especially multiple choice, is if you're only given one number, that's often the number you're going to need to start your mental math with. And so to start setting it up from there, we have 14.2 grams P4O10, and they want to know how much oxygen in moles is needed to get there. There's no mention of how much phosphorus we have, so we can assume that there's plenty of phosphorus around. It's not going to run out or anything. And we want to see if we can get from grams of P4O10 to moles of oxygen. Well, according to this reaction equation, we've got a ratio that's going to let us connect those two things, the oxygen to the phosphorus, or P4O10 there. We have a 5-to-1 ratio, so we're good to go on that. Question is, can we turn that into a problem that we can do with mental math, and only that? So we're going to get to moles first. 1 mole of P4O10 has a certain mass. You can go to the periodic table and add this up, ballpark it, as always with this, or as you notice in this problem, they've gone ahead and given us the molecular weight, assuming that you'll be able to know what to do with it. So 284 grams per mole of that substance, given right there in the context of the problem. Save yourself the trouble, use the numbers that they gave you. Now, those numbers go together nicely in that we have 284 and 142. As I've mentioned to you perhaps in class before, you want to ignore decimal points, at least at first, to see if you can find some simple relationships between the numbers that you have. In this case, again, 142 and 284 are multiples of 2 apart. We're going to double 142 to get to 284. So just for the time being, I'm going to encourage you to use this strategy if it helps you. Move the decimal over for a second, just momentarily, to get 142. And then basically we're saying 142 divided by 284. Well, 142 or 284 is exactly half, 0.5, right? But in that, my answer, to come out of that part, 0.5 rather, I need to go ahead and move that decimal back. Since I moved the decimal over initially to the right, we need to move it back to the left in order to get to the actual answer that we've got. So moving that decimal back over to the left, I get 0.05 moles of P4O10. And then from there, we're going to take that times our mole ratio. So we've got 5 moles of oxygen for every 4 moles of, or sorry, 1 mole of our compound P4O10. So 5 moles O2 for every 1 mole of our compound. 5 times 5 here is 25. That's not exactly the numbers that we have, 5 and 5, but if you simply look at 0.05 times 5, you're basically multiplying 5 times 5. And the only number that has 5 times 5 equals 25 as a possible option, and is D, the only choice that has that 25 in it, as you think about pulling those non-zero numbers out of a calculation to do the math in your head. So we're focusing on here 5 times 5 equals some kind of 25 value. It's not exactly 25, but those numbers need to be in our answer, and 250 or 0.250 moles in this case would also be an option for the correct answer, and it's the only correct answer for this one. So the strategies for this one, couple of strategies, is the temporarily move your decimal one direction, do the math, and then move your decimal back the other way in your answer. Okay? I did that here. Again, I took initially and moved my decimal point to the right to get 142. Then I was able to relate that, as you see up here, okay, to 284 and get an answer as a half, or 0.5. But then I went ahead and moved that decimal right back again, okay, to put it back where it belonged. That was the step we did over here. So initially moved it to the right, did the calculation here in my head, or hopefully in your head, and then move the decimal back to the left again to put it back where it belongs. We kind of have to conserve those decimal movements in our answers. When we only do it to one value, we have to bring that back in our answer. And we'll see more of those strategies as we go into some of the others. So let's look at number 4. Here we have a question about a class of compounds that are in organic chemistry are called alkenes. We're not going to do much with organic chemistry, but alkenes are simply compounds that have a double bonded carbon to another carbon somewhere in the formula. They're telling us that alkenes in general have a formula of CnH2n. So like C2H4 or C3H6, something like that. Those would be the alkene compounds. And so for our purposes here, we're going to write a balanced equation for the combustion, which is what this is talking about, burned. We're burning an alkene. So I'm going to go ahead and burn an alkene in oxygen. So the formula, we're going to have some CH compound with oxygen to make, as always with combustion, CO2 and water. And they're telling us that they know the formula of our alkene in general, CnH2n. Let's just go with the simplest one we've got. That would be make N1, and that would give us C1H2. So for a simple combustion equation to model how alkenes would burn, this is that equation, a general equation for any alkene. Now, it's not balanced, so let's make sure and do that. Let's make sure and check that it's balanced. So 1 carbon on each side, 2 hydrogens on each side. So the carbons and the hydrogens are relatively easy to balance. That gives us, let's see, 3 oxygens on the right, so we're going to need like 1.5 oxygen molecules. And that's a really, really simply balanced equation. Now you might think, well, how can I just balance the equation when I don't even know the formula of the alkene? It doesn't matter, it turns out. The general formula lets us balance it, and if we were to change that N value to 2 or 3 or 4, it would give us a bigger, more complicated alkene molecule and a formula to go with it, but it would also change the coefficients proportionally, and you find out the same answer would come out of this no matter what multiple you put in there as your value for N. So don't worry about N being 1 or 2 or any other number. You can plug in a different number and try it if you're itching for something to do. But what they're getting at here then is that if we to burn 0.561 grams of an alkene, according to this example reaction, how many moles of water would be formed? So let's set that up. 0.561 grams of my CH2, which is my general formula. We need to be able to relate that to eventually a water. So we're trying to get over here and solve for water at the end of this problem. We need to get to moles first. So 1 mole of our generic CH2 alkene would have a mass, let's see, carbon's 12, 2 hydrogens makes another 2, so a total of 14 grams of CH2. And then to get to moles of water, which is what they want us to do, we go back to our balanced equation and see that, well, for every 1 mole of water that we produce, we're going to use 1 mole of our generic CH2 compound. Now, how to get an answer from here? I've got some numbers here again to work with that maybe aren't real obvious mental math numbers for me. 561 and 140 is what I'm looking at here. Or 561 and 14. It doesn't really matter if you think about it as 14 or as 140. If I'm going to try to think about pulling those numbers out and working them together as mental math, what I need to look for is, as I've heard on many videos before, expect some easy math. Okay, so let's see if we can find some easy math in this particular problem. What we've got here then is 561 over 140. Now, if you can, feel free to go ahead and round things a bit to make your life a little bit easier. And in this example, I would say treat 561 as 560 because they're basically the same. 0.561 versus 0.560. That's not going to make the difference in your answer, right? And if we do that, right away, what I can do here is I can get those zeros out of there. Take the zeros off and call this 56 over 14. And now if I'm good at simplifying, I might be able to jump right in and do this rather quickly, or do it in stages. It turns out that 14 can be multiplied times 4 to get 56. If you don't see that right away, find some other multiple, or a rather common factor that you know you can factor out of both of those, and simplify it down. Maybe you'd look at that and see, well, I think 7 goes into both of those. And you're right, 8 over 2, which then hopefully you turn into 4 over 1, or simply an answer of 4. Now, that takes us pretty far to the answer. That takes us pretty close, okay, and gets us in the neighborhood of 2 of our choices, right? We've got 2 answers that have 4 in them, so we can eliminate the other 3 answers around them, okay? And from there, it's a matter of kind of playing around with, are we talking about 0.4 moles, or are we talking about 0.04 moles? Now, how do I reconcile that? Look back at the original numbers. Look back at the original sizes of these numbers. You're dividing by 14. You're dividing a number by 14. One of our 2 choices over here that are still alive as our options, one of our 2 choices here is 0.40. That's about a half, approximately 1/2 of a mole. Now, we're not dividing, say, 7 by 14. That would give us pretty close to a half. 0.561 isn't anywhere near half of 14. So the answer that comes out of the calculator, if I could use one here, shouldn't be anywhere near half. That kind of helps me eliminate 0.4 as an answer. But it leaves me just one choice as the correct answer, and that's my 0.04 moles, the very first answer that's there. Again, that was sort of an estimation idea that helps us or forces us to think, is this answer close to one of those choices, or can I rule one of them out clearly? It turns out that 5.61 over 14 would give me that 0.4 moles that we ruled out as choice D. That's not what we had here. Because we had 0.561, that moved my decimal over once more and left me with only one good realistic choice. In this case, some quick math, some quick reduction. We got rid of that 1 on 561 and made it a 0. That made it a lot easier for us to reduce that down, get rid of the zeros, found a common factor of, say, 7 or 14, and got it down to an answer that has 4 as the main non-zero value in the answer. And that's important to reconcile, or recognize rather. Let's do one more here, number 5. So now they've given us the equation, it's even balanced. That's awesome. Saves us a lot of trouble. Makes us jump right into the problem and think about the moles. They're telling us that we have silver and nitric acid, according to this reaction, 0.1 moles of silver and 10 milliliters of 6 molar nitric acid. Then they're asking us to figure out the amount of another substance, in this case, the moles of NO that can be formed. So this is a classic example of, one, it's stoichiometry, because we're starting with one thing and solving for another. But even more than that, we want to recognize number 5 here as a limiting and excess reactant problem. You need to be able to figure out, of the 2 amounts that they gave you, which are the 0.1 moles of silver and the 10 milliliters of 6 molar nitric acid, which of those is my limiting reactant, and how will that affect my work? How will that affect my actual answer? Now, I don't like how they've got the equation crowded up there. I'm going to go ahead and pull it down here so we can use it a little bit more easily. 3 silvers plus 4 HNO3s. As I do that, since I know the equation was balanced, I'm not going to write the whole thing. I'm going to only isolate and use the parts I actually need for my work in this problem. Since it's balanced already, I can sift out the stuff I don't need and leave just the 3 parts that actually matter to us in this problem. That's the silver, the nitric acid, and the NO. Those are the 3 parts that are actually in play. So for you to solve this problem, I just kind of left out the other stuff. Do that. Once the equation is balanced, you probably don't care anymore about those. So cross them out temporarily and leave them out of your distraction. Okay. Now, let's see how we got for moles here. We know we have 0.1 moles of silver. That's 0.1 moles here. And for the other one, we need to do a little multiplication. Because as always, with moles on a solution, it's volume times molarity to get moles. Volume times molarity. Now this is a molarity of 6 and a volume of 10 milliliters. But in order to solve this way and compare moles to moles, we're going to want to get those milliliters into liters. So really for this, to find the moles out of here, we're going to take 6 moles per liter and multiply it by the number of liters we have, which is 10 milliliters, 0.01. And that's enough. We don't need to worry too much about decimal places when we're doing multiple choice almost all the time. 6 times 0.01 is 0.06. 0.06 moles of the nitric acid. I'm going to jot that down here. Now comes the most important part of eliminating an excess reactant problem. You want to be able to look at this and figure out rather quickly, but carefully, which of these two is the limiting and which is the excess reactant. We only care mostly about the limiting reactant. We want to identify the limiting reactant and use it. You can't always look at the values that you have and just pick the smaller one to be the limiting reactant, because sometimes the smaller one isn't limiting. Based on the mole ratios, that can mess things up a little bit. But let's look at what we have here as far as our mole ratios and our coefficients in this equation, and the amounts that we have available to us. For this silver, since it's a 3-to-4 ratio, if I'm going to use 0.1 moles of silver, and it's a 4-to-3 ratio, I'm going to need 4 parts of nitric acid for every 3 parts of silver, which means I'm going to need more moles of nitric acid than I am of my silver. 4 parts for every 3 means I'm going to need more moles of nitric acid than I am going to need or use of my silver. And I don't have more moles of nitric acid available, right? I've only got 0.06 moles. That's not enough, because I'm going to automatically be able to tell, based on that mole ratio again, that 4-to-3 means I'm going to need more moles of nitric acid than I am of silver. And so I'm going to rule out nitric acid. I'm going to rule out silver as my limiting reactant. I'm going to assume it's the other way around. But let's just double check and make sure we can prove it with a quick kind of confirmation of that by the math. Okay, and so what I mean by that is, let's take a look. For me to use 0.06 moles of HNO3, based on a 3-to-4 ratio, 3 silvers for every 4 nitric acids, I'm only going to need 3/4 as much of that. What's 3/4 of 6? Well, that's 4.5. 3/4 of 6 is 4.5. And so that turns out to be 0.045 moles of silver needed or used. Okay. And that proves for me, I don't have to do that math, but it's going to help me understand for sure that the nitric acid is the limiting reactant. Since I have this amount available, in fact I have more than that, quite a bit more than that, that means the silver will not run out and the nitric acid will. And we can base our math then on the nitric acid from there. Okay? So if this is my limiting reactant, that's the one I want to use to kind of think from there on what my final answer is going to be. If I use up my 0.06 moles of HNO3, and I look at my mole ratio once again, it's a 4-to-1 ratio with the NO, which is what this problem is asking us about. Okay. Which means that I'll make 1 mole of NO for every 4 moles of nitric acid. What's 1/4 of 6? Well, half of 6 is 3, half of that is 1.5, so 0.015 moles of NO is what we'll make. 6/4, or 1/4 of 6. We want to be able to think about things like that. And you notice I'm not saying what's 1/4 of 0.06. Forget the zeros temporarily, take them out of there, and then put them back into your answer. So what I've kind of done is I'm saying 6 times 1/4. And if you can think of, do a half and then a half, if that works better for you, that's 1.5, right? Well, since I used 6, that means I initially must have moved my decimal over twice. Now I got to move it back twice. So back over twice gives me 0.015 moles. And my answer then for this question would have to be A. So that's the idea on some of these mental math questions. I don't want this video to get too long, so I'm going to make a series here. I'll just make maybe 3 videos on this topic, and then you can watch them as you need it. That covers us with 3, 4, and 5. I'll stop there and get to work on the next video for you on starting with the next questions on our list. We'll see you then.